The calendar says March. The atmosphere didn't get the memo. Tonight, across 9 states, the air is drier than the Sahara Desert. Winds are tearing through Wyoming at 70 miles per hour, and the National Weather Service is using language, in March, that forecasters normally reserve for the worst days of August. 16 red flag warnings, 5 fire weather watches, a dry thunderstorm risk meaning nature itself may provide the ignition. Colorado and Utah just recorded their lowest snowpack in history. Over 80% of monitoring stations are in drought. This isn't a heat wave that got a little out of hand. This is something the historical record has no clean category for. A system that was supposed to arrive in summer showed up 90 days early, and it brought everything with it. Stay with me, because everything seems to be aligning to something, and tonight we are going to show you, piece by piece, exactly how. If you find yourself drawn into what we cover here on Project Nightwatch, go ahead and hit like and subscribe, because what assembled this fire weather event did not happen overnight, and neither will the story of where it leads. Drop a comment below with where you're watching from, what time it is there, and your honest read on whether March should be capable of doing this. Now settle in, because we are just getting started. Part 1. The warning they don't issue in March. Something is wrong with the calendar. Not metaphorically, not philosophically. Literally, physically wrong, in the way that a thermometer reads 105 degrees in a room that's supposed to be air-conditioned, and you stand there staring at it trying to figure out if the thermometer is broken or if something in the room has fundamentally changed. That is the feeling inside National Weather Service offices this morning, because the alerts sitting on forecasters' screens right now are not March alerts, they are not spring alerts, they are not even early summer alerts. They are the kind of alert stack that gets generated in late July when the West has been baking for 3 months straight, when every river gauge is dropping, and every fuel moisture reading is screaming and the whole system is coiled and ready. And yet here we are, March 30th, 2026, and the National Weather Service has just issued 16 red flag warnings and 5 fire weather watches across 9 states simultaneously. 16. Let that number sit for a second. On a random Tuesday in late March, the Storm Prediction Center, the same agency that tracks tornadoes and severe thunderstorms, the people who issue the bulletins that make emergency managers pick up the phone, has declared a critical fire weather risk across a corridor that stretches from the Canadian border in Wyoming all the way down to the Texas Panhandle. That is roughly 1,500 miles of contiguous American land where, as of this morning, the official government forecast is conditions are suitable for rapid and erratic fire spread. That language, rapid and erratic fire spread, is not casual. Forecasters are trained to be conservative. They are trained to understate. When the National Weather Service uses words like rapid and erratic in the same sentence, they are telling you, in the most professionally restrained way they know how, that they are genuinely alarmed. Now here is the number that should stop you cold. The relative humidity forecast for Monday afternoon across the core of this corridor is 8%. 8. Not 18, not 28. 8% relative humidity. Let me give you some context for that number, because it is easy to hear a percentage and not feel it. The Sahara Desert, the largest hot desert on the planet, the place that exists in the human imagination as the definition of absolute dryness, averages relative humidity somewhere between 15 and 25% during the day. Death Valley, California, in July, at the absolute peak of its legendary summer heat, routinely sits between 10 and 15%. 8% humidity is drier than both of those places at their driest. If you were standing in that corridor Monday afternoon, the air itself would be pulling moisture out of your skin faster than you could replenish it. It would be pulling moisture out of the grass, out of the brush, out of every dry stem and dead leaf sitting on the ground, already stressed from a winter that never really showed up. And into that environment, the Storm Prediction Center has also flagged something that almost never appears on March fire weather outlooks: an isolated dry thunderstorm risk. We will come back to what that means in precise scientific terms, but the short version is this. The atmosphere may be about to produce lightning without rain. It may be about to strike a match over a landscape that has already used up every fire break it had. The wind gusts forecast for Wyoming's Cody Foothills region top out at 70 miles per hour. 70. That is not a wind event that slows a fire down. That is a wind event that turns a fire into something that behaves less like a fire and more like a weather system in its own right. Sustained winds of 30 to 40 miles per hour are forecast across the entire 1,500-mile corridor, and that sustained number matters more than the peak gusts in some ways, because sustained wind means continuous oxygen delivery, continuous fuel drying, continuous ember transport, hour after hour after hour. Firefighters do not fight fires in 40-mile-per-hour sustained winds. They pull back, they evacuate, they watch. What makes this genuinely extraordinary, and I want to be precise about this, because this is the thing that separates today from every other fire weather event you have ever half paid attention to, is not any single one of these numbers. It is that all of them are happening at the same time, in the same place, in the same atmospheric window. And that window opened in late March. The fuel moisture readings across this corridor are sitting at or above the 90th percentile for dryness. That means these fuels are drier than they are on 90% of all days in the entire historical record, and that record includes every peak summer month. July, August, the height of fire season. The fuels on the ground right now in late March are drier than they have been on the majority of the worst fire weather days ever recorded. The warnings extend overnight. That detail is easy to skip past, but it matters. Red flag warnings in March are already unusual. Red flag warnings in March that persist through the overnight hours, when temperatures typically drop and humidity typically recovers, that is the system telling you that no reset is coming. There is no cool, damp morning relief waiting on the other side of tonight. And here is the open question that hangs over all of this. All of these conditions, the warnings, the wind, the humidity, the fuel dryness, they describe a system that is primed. They describe a system that is ready. But a system that is ready still needs a spark. It still needs ignition. And in most fire weather events, ignition is the human variable. A downed power line, a discarded cigarette, a spark off a trailer hitch, and that human variable can, at least theoretically, be managed. Campfire bans, power shutoffs, public warnings. None of that addresses what the Storm Prediction Center just put on the map this morning, because today, ignition may not come from people. Part 2, the physics of an unstoppable fire. Once you understand what 8% relative humidity actually does to vegetation at the molecular level, the fire weather warnings stop feeling like bureaucratic caution and start feeling like physics announcements. Every piece of organic material, every grass stem, every dead branch, every layer of leaf litter on the ground is constantly exchanging moisture with the surrounding air. It gives moisture up when the air is dry and absorbs it when the air is humid. This exchange process has a rate, and at 8% relative humidity, that rate becomes essentially one-directional. The air is so dry that it is pulling moisture out of organic material faster than any natural process can replace it. Foresters and fire behavior analysts measure this through something called equilibrium moisture content, the moisture level that a fuel will reach if you leave it sitting in a given atmospheric condition long enough. At 8% relative humidity, fine fuels, the grasses and small sticks and dry leaves that actually carry fire, reach their equilibrium moisture content in roughly 1 hour. 1 hour of sitting in this air, and the vegetation is essentially as dry as it is going to get. Now connect that to the energy release component, which forecasters call the ERC. The ERC is a calculated index that estimates the available energy per unit area in a fire, essentially how much fire the fuel bed can produce if it ignites. When the ERC sits at the 90th percentile, as it does across this corridor right now, in late March, it means that the potential energy in these fuels is higher than it has been on 90% of all recorded days, including peak summer days. The fuels are not just dry, they are at a state of dryness that most forecasters associate exclusively with deep summer drought conditions, and they have reached that state months ahead of any historical baseline. And that is not a coincidence. That is the result of a winter that systematically failed to deliver the moisture recharge that these ecosystems depend on. We will come back to exactly how that happened. But first, understand what it means for fire behavior today. Wind and fire have a relationship that most people intuitively understand but dramatically underestimate in terms of scale. Wind does 3 things to a fire simultaneously. First, it delivers oxygen, the oxidizer in the combustion reaction, faster than any natural convective process can. More oxygen means faster, hotter combustion. Second, wind tilts the flame toward unburned fuel ahead of the fire, preheating that fuel and reducing the energy the fire needs to ignite it. The fire becomes more efficient with every gust. Third, wind transports embers. A single ember lofted by a 30-mile-per-hour wind in dry conditions can travel more than a mile before landing. If it lands on receptive fuel, and at 8% humidity, essentially everything is receptive fuel, you now have a spot fire a mile ahead of your main fire front, before any ground crew can reach it, before any air tanker can be retasked to it, and that spot fire starts throwing its own embers. Grass fires under these conditions can spread at speeds approaching 5 miles per hour. 5 miles per hour sounds slow until you remember that a firefighter walking quickly through rough terrain manages maybe 2 miles per hour. In the time it takes a crew to establish a fire line, the fire can outflank them, surround them, and cut off their escape route. This is not a hypothetical. It is a documented fire behaviour pattern that has killed firefighters in conditions less extreme than what is forecast today. There is a concept in fire behaviour science called a plume-dominated fire, and it is the threshold beyond which suppression becomes essentially impossible. In most fires, the wind determines fire behaviour, the fire spreads in the direction the wind pushes it, more or less predictably. In a plume-dominated fire, the fire itself generates so much heat that it creates its own convective column, its own updraft, its own localized weather. The fire starts making decisions that have nothing to do with the background wind. It can throw embers in directions opposite to the surface wind. It can create sudden explosive runs in any direction. Suppression resources, aircraft, engines, hand crews are designed and trained around fires that behave predictably. Plume-dominated fires do not behave predictably. They behave like something that has stopped following the rules. Here is the distinction that matters most for today. There is a difference between ignition probability and propagation certainty. The question of whether ignition will occur today is genuinely uncertain. Maybe every human source of ignition is successfully controlled. Maybe no power line comes down. Maybe every campfire ban is respected. The ignition probability is less than 100%. But the propagation certainty, the certainty that any ignition which does occur will spread rapidly, intensely, and in ways that are difficult or impossible to contain, that is not uncertain. That is baked into the physics. The 8% humidity, the 90th percentile ERC, the sustained 40-mile-per-hour winds, these numbers do not describe a landscape where fires might spread. They describe a landscape where fires will spread. The only open variable is whether the first spark appears, which brings us to the part of today's forecast that removes the human variable entirely. Part 3. The ignition problem. No one can control. A dry thunderstorm is one of nature's most counterintuitive phenomena, and understanding it requires letting go of the mental image most of us carry of what a thunderstorm is. When most people picture a thunderstorm, they picture rain. They picture the kind of afternoon deluge that clears the air, drops the temperature, and leaves everything smelling like wet earth. Lightning, in that picture, is secondary, dramatic, yes, potentially dangerous, but happening against a backdrop of moisture, of wetness, of suppression. The lightning and the rain arrive together. That is the normal contract. A dry thunderstorm breaks that contract completely. The technical term for what makes it possible is virga, precipitation that falls from a cloud but evaporates before it reaches the ground. And the atmospheric conditions that allow virga to occur are, unfortunately, precisely the atmospheric conditions that produce extreme fire weather. When the lower atmosphere is intensely dry and hot, as it is across this corridor today, falling precipitation encounters that dry air layer and converts back to water vapour before it can reach the surface. The cloud looks like a thunderstorm. The radar shows precipitation. There is lightning because the electrical charge separation inside the convective column is real and the discharge is real. But the rain never arrives. What arrives is the lightning only. The mechanics of why this happens in today's setup involve what forecasters call high-based convection. In a moist atmosphere, clouds form relatively low to the ground, and the distance falling rain must travel through dry air is short. The precipitation makes it to the surface. In today's atmosphere, which is not just dry at the surface but dry through a substantial portion of the lower troposphere, the cloud bases are unusually high. Rain falling from those high bases must travel through thousands of feet of bone-dry air before reaching the ground. At the temperatures present today, it does not make it. So you have an atmosphere that is generating electrical discharges, lightning strikes, with essentially zero natural suppression accompanying them. In a normal thunderstorm, even if lightning starts a fire, the rain that follows often mitigates the immediate spread. The fuels get wet, the humidity spikes locally, there is a natural dampening effect. None of that exists in today's setup. Lightning strikes a dry grass field, no rain follows, the humidity around that new ignition point is 8%, the wind is blowing at 40 miles per hour. What happens next is not a question of fire behaviour modelling, it is arithmetic. The Storm Prediction Centre does not casually flag dry thunderstorm potential. It appears on outlooks when the specific combination of atmospheric instability and lower-level dryness crosses a threshold that forecasters recognise as genuinely dangerous. Today it is not only flagged, it is flagged across a corridor that is already sitting at peak fuel dryness and peak wind conditions. The probability framing matters here. Even if the dry thunderstorm coverage is described as isolated, meaning not widespread, not guaranteed across every county, isolated coverage over a 1,500-mile corridor still means dozens of potential strike points. A single storm cell moving across eastern Wyoming can produce hundreds of lightning strikes in a matter of hours. Even a small fraction of those strikes, landing on receptive fuel with no rainfall suppression, represents multiple simultaneous ignition events. This is the scenario that removes the human variable from the fire weather equation. Every public-facing wildfire prevention campaign is built on a foundation of human behaviour modification. The Smokey Bear campaign, fire bans, utility power shutoffs in high wind periods, public education about trailer chains and campfire safety. All of that infrastructure of prevention is designed to address the human causes of ignition. It has no mechanism, no lever, no strategy that applies to dry lightning. You cannot ban a thunderstorm. You cannot shut off the atmosphere's electrical system as a precautionary measure, and today, the atmosphere itself is the ignition risk. History offers a few precedents for what happens when dry lightning sweeps across a primed fuel bed at scale, and none of them are reassuring. The August 2020 California lightning siege produced over 10,000 lightning strikes over 72 hours during a period of exceptional dryness, igniting hundreds of fires simultaneously and overwhelming suppression resources so completely that several fires burned for months. That event occurred in August, peak fire season, over a state that had already been baking for most of the summer. What is happening today is a March version of that setup, compressed in time and laid over a corridor that stretches from Canada to Texas. The operational nightmare scenario is not one fire, it is 20 fires starting simultaneously across 5 states, because the moment that happens, the mutual aid system, the network through which states and federal agencies share firefighting resources, hits its ceiling. There are only so many air tankers, there are only so many Type 1 incident management teams, there are only so many hotshot crews. When the requests come in simultaneously from Wyoming, Colorado, Kansas, Oklahoma and Texas, the answer to most of them is, we are already committed elsewhere. Stand by. Imagine that scenario playing out across 1,500 miles of corridor, except you do not have to imagine it, because the conditions for it are on the forecast maps right now, and this synchronized, continental-scale alignment of fire weather conditions did not appear from nowhere. It was assembled piece by piece over months. Part 4, the 1,500-mile fuse. Pull up a map of the central and western United States and draw a line. Start it in northern Wyoming near the Montana border. Run it south through eastern Wyoming, into western Nebraska, through Colorado, into Kansas, down through the Oklahoma Panhandle, and terminate it in the Texas Panhandle. That line is approximately 1,500 miles long, and right now every inch of it is under the same fire weather regime. That alignment is not normal. Most significant fire weather events are regional, a high-pressure system pushing dry air into the southwest, a wind event isolated to California's coastal ranges, a drought pattern concentrated in the Great Plains. The atmospheric conditions that produce dangerous fire weather are usually heterogeneous. They peak here, ease there, create a patchwork where stressed areas are at least adjacent to areas with recovery potential. The resource allocation system for firefighting is built on that heterogeneity. It assumes that if Arizona is burning badly, resources from Oregon or Utah can be mobilized. It assumes geographic spacing between major incidents. Today's setup eliminates that spacing over a corridor covering parts of Wyoming, Nebraska, Colorado, South Dakota, Kansas, Oklahoma, Texas, and New Mexico. Red flag warnings are not scattered across this area, they are contiguous. The relative humidity values, the wind speed forecasts, the energy release component readings, they are consistently extreme from the northern anchor to the southern terminus. This is not multiple regional warnings that happen to coexist on the same calendar day. This is one atmospheric system expressing one set of extreme conditions across 1,500 miles of connected geography. The atmospheric pattern responsible for this alignment is a large-scale ridge, a dome of high pressure over the western United States that has been steering Pacific moisture systems northward and away from the interior for weeks. High-pressure ridges are normal features of the atmosphere. What is unusual is the combination of their persistence, their timing relative to the seasonal calendar, and the fuel state they are presiding over. The ridge has locked a dry, warm air mass over the central corridor at exactly the moment when that corridor's fuels, already depleted by a failed winter and months of drought, are sitting at peak summer dryness in late March. Compare this to landmark fire events of the past. The 2012 High Park Fire in Colorado, the 2017 Eagle Creek Fire in Oregon, even the 2018 Camp Fire in California. Each of these was a regional event, a state-level emergency, devastating in its own right, but contained in geographic scope in a way that allowed the national mobilization system to function. Resources flowed from unaffected regions to the emergency zone. The national system absorbed the shock. The concept of continental synchronization, multiple regions peaking simultaneously, has appeared in climate and fire behavior research as a future risk scenario. The concern in that research is not that any single fire will be larger than historical precedents. The concern is that the resource allocation system will be overwhelmed by simultaneity. A dozen major fires starting on the same day across a 1,000-mile corridor does not produce a proportional response. It produces a triage system, where some fires simply do not receive suppression resources and burn until conditions change naturally. Stretching east from this corridor, the moisture signals are also not encouraging. Parts of the Midwest are carrying subsurface moisture deficits that make them more susceptible to rapid fuel drying during wind events than their surface conditions suggest. The eastern extension of today's critical risk is a signal that the fire weather corridor is not firmly bounded at the edges drawn on today's maps. It is the visible expression of a much broader atmospheric state that extends well beyond the formal warning zones. What we are looking at today is a system behaving as a single organism, one unified zone of extreme fire weather potential, stretching across the interior of the North American continent. And the critical insight, the thing that separates this from a bad weather day, is that systems of this kind do not fail instantly. They fail over time. The conditions on March 30th did not materialize this morning. They were constructed layer by layer over a period of months. And to understand why today is happening, you have to understand what did not happen this past winter. Part 5. The winter that didn't exist. There was supposed to be a winter. In the mountains of Colorado and Utah, winter is not just a season, it is a storage system. Every storm that crosses the Rockies from November through March is depositing a check into a moisture account that the entire downstream ecosystem, the rivers, the soil, the vegetation, the aquifers, draws on from April through August. Snowpack is the mechanism by which the West gets its water on a delayed payment plan. The snow falls, accumulates, and then melts slowly and steadily through the spring and early summer, releasing moisture into the soil gradually over weeks and months rather than dumping it all at once in a flash flood. That slow, steady release is what keeps soils moist in May. It is what keeps vegetation from desiccating in June. It is what pushes the transition from spring green to summer brown later into the year, buying time before fire season peaks. This past winter, that check was never written. Colorado and Utah recorded the lowest snowpack in their instrumental records, records that in some locations extend back more than a century at multiple points during this past winter. The snow water equivalent measurements at SNOTEL stations across the two-state region, which track exactly how much water is stored in the snowpack at any given moment, were catastrophically low. More than 80% of SNOTEL monitoring stations were reading drought conditions. Not low, not below average. Drought. Satellite imagery of snow cover across the mountain west in January and February 2026 showed anomalies consistent with conditions not seen since the early 2000s, when the West entered the extended drought period that climatologists have characterized as the worst in over 1,000 years. The implications of that snowpack failure for what is happening today are direct and mechanical. When the snowpack does not accumulate, the spring melt does not occur. When the spring melt does not occur, the soils do not receive their moisture recharge. When the soils are not recharged, the grasses and shrubs and forbs that rely on that soil moisture cannot maintain their tissue moisture content through the late spring and early summer transition. They dry out earlier. They reach critical dryness earlier. The vegetation that would normally be green and fire-resistant in late March and April is instead showing fuel moisture readings more consistent with July. Think about what that means for the central thread of this story. March 30th is behaving like a peak fire weather day in late summer, not because the atmosphere has done something impossible, but because the fuels beneath the atmosphere have lost months of their normal moisture buffer. The winter moisture recharge that should have pushed the earliest possible extreme fire weather into June or July never happened. The buffer was not there. And when the atmospheric trigger arrived, the heat wave, the dry air, the wind, there was nothing underneath it to absorb the blow. This is what climate scientists mean when they describe hydrological failure as a fire risk amplifier. It is not just that the water is missing. It is that the water's absence compresses the timeline of fire risk forward in the calendar by weeks or months. And the system primed on March 30th is the direct result of that compression. Part 6. Fuel moisture. The invisible disaster. If you want to understand why the fire weather conditions of March 30th are as extreme as the forecasters say they are, you need to spend a moment inside the numbers that most fire weather explainers skip over. Because the energy release component sitting at the 90th percentile in late March is not just a high number, it is a number that should not be possible at this time of year under any normal climate conditions. And understanding why it is possible is understanding the invisible disaster that has been unfolding in slow motion since last autumn. The ERC is calculated from a combination of dead fuel moisture, live fuel moisture, and precipitation history going back weeks. Dead fuels are exactly what they sound like. Dead vegetation, the grasses and woody debris that have no living tissue maintaining moisture content. Dead fuels respond quickly to atmospheric humidity changes. In dry air, they lose moisture fast. In humid air, they gain it back. Live fuels, grasses that are still biologically active, shrubs, trees, also respond to atmospheric conditions, but they have a biological mechanism for resisting drying. They can pull moisture from deep soil layers. They can close their stomata to reduce water loss. They have defences, but those defences depend on the deep soil moisture being there to pull from. And after a winter, with no snowpack and months of drought, the deep soil moisture is not there. The live fuels across this corridor have been drawing down a soil moisture account that was already in deficit when autumn ended, and that account has now run dry. The live fuels are behaving like dead fuels. Their biological defences have been overwhelmed by the cumulative moisture deficit of the past 6 to 8 months. The lag effect in live fuels is normally a critical safety buffer in fire behaviour. Even on extreme fire weather days in summer, the fact that trees and shrubs retain significantly higher moisture content than dead fuels means they resist ignition. They do not carry fire as readily, and they create natural breaks in fuel continuity that slow fire spread. When live fuel moisture collapses, as it has across this corridor this March, that buffer disappears. The fire behaviour analyst looking at the fuel state today is not seeing a spring fuel bed with some stressed areas. They are seeing a fuel bed that has essentially preloaded to peak summer configuration in every category simultaneously. The phrase I keep coming back to for this is invisible drought inside the vegetation. The landscape does not look like tinder from the outside. There are still brown grasses that look like normal late winter grasses. There are shrubs that are not visibly dead. But the moisture content inside those fuels has crossed below the thresholds at which ignition becomes not just possible but likely, and below which fire spread becomes not just probable but near certain under these wind conditions. The disaster is inside the plant tissue. It is not visible from a car window or a satellite image or a news camera. It is only visible when you look at the fuel moisture measurements coming off the monitoring stations, and those measurements are screaming. This is the second layer of the system failure that made March 30th possible. The snowpack failure was the foundational collapse. It removed the moisture recharge that should have kept soils and fuels protected through the late winter and early spring. The fuel moisture collapse is what that foundational failure looks like inside the vegetation itself. And together, they mean that by the time the atmospheric trigger arrived today, the fuels were already at a state of readiness that in any other year would only be achieved by mid-July at the earliest. Part 7. The drought that quietly took over. Something else has been happening quietly in the background, and it matters to why March 30th is possible. As of the most recent drought monitor data, 56% of the lower 48 states are in some degree of drought. That number is not concentrated in the West, where drought is a familiar, if unwelcome, presence. It has spread. The Great Plains, parts of the Midwest, sections of the Southeast, all carrying subsurface moisture deficits that do not always show up in surface conditions, but that absolutely show up in fuel moisture readings, in soil behaviour during heat events, and in the speed with which vegetation dries when the atmosphere turns hostile. This matters to the central story because the drought is the slow-moving baseline beneath everything happening today. The atmospheric trigger on March 30th, the wind, the heat, the dry air, would be a significant fire weather event in any year. But overlaid on the drought conditions currently affecting more than half the country, it becomes something of a different character. The drought has removed the resilience from the system. It has reduced the margin between normal stress and catastrophic stress to essentially zero across a continental scale area. When the atmospheric trigger arrived, there was no buffer, no recovery, no cushion. Just a landscape that had already spent every reserve it had, and today is when that spending came due. Part 8. The heat wave that finished the job. In the weeks leading up to March 30th, 14 states recorded temperature anomalies of 10 to 20 degrees Fahrenheit, above their historical March averages. 10 to 20 degrees above normal is not a warm spell. It is not an early spring. It is a heat event that, if it occurred in summer, would trigger excessive heat warnings and public health advisories across multiple states. Occurring in March, in a region that normally still has snowpack on the ground and frost in the morning, it is something the climate record has essentially no precedent for at this scale. Heat accelerates every process that makes fire weather dangerous. It drives atmospheric moisture demand. The capacity of air to hold water vapour increases exponentially with temperature, which means hot air pulls moisture out of fuels and soils faster than cool air. It accelerates the evaporation of what little soil moisture survived the winter. It extends the low humidity window of each day, reducing the hours during which fuels can recover from the previous day's drying. And it does something that most people do not think about. It changes the thermal properties of the soil. Soil that has been exposed to sustained above normal temperatures stores heat in a way that resists the typical overnight cooling cycle. The mornings are warmer than they should be. The overnight humidity recovery, the natural reset that normally prevents fire weather from being a continuous, round-the-clock threat, is compressed and weakened. The relationship between heat and fire is not direct. Heat alone does not start fires and does not even necessarily create the most dangerous fire weather conditions. What heat does is amplify. It takes a drought-stressed fuel bed and accelerates the final drying. It takes an already low humidity air mass and pulls it lower. It takes a wind event that would otherwise be a significant but manageable fire weather situation and converts it into something that pushes past the upper boundaries of what suppression systems are designed to handle. Here is the layering that matters for today. The snowpack failure was the foundational collapse. It happened over the winter and set the moisture deficit in place. The drought was the background condition that maintained and deepened that deficit through the autumn and early winter. The heat wave was the final atmospheric push, the last element needed to bring the fuel dryness from concerning to unprecedented for this time of year. Each layer built on the previous one. Each failure made the next failure more likely and more severe. And on March 30th, the atmospheric trigger, the cold front approaching from the northwest, driving winds and dropping humidity to historic lows, arrived over a system that had already been systematically stripped of every defense it possessed. This is not an event that started today. Today is just the day the failure became impossible to ignore. Part 9. The cold front paradox. Here is something that sounds wrong until the physics clicks into place. The system responsible for the most dangerous conditions today is technically a cold front bringing relief. That front is approaching from the northwest, carrying cooler air that will eventually moderate temperatures and in some areas bring precipitation. It is, in the most literal sense, an improvement on the way. And it is also right now actively making everything worse. Cold fronts create fire weather through a mechanism that meteorologists call the pressure gradient effect. As a cold front approaches, the pressure difference between the cool air mass behind it and the warm air mass ahead of it drives wind. Strong fronts drive strong wind. The particular geography of today's setup, the corridor from Wyoming through the Texas Panhandle, channels and accelerates that wind in ways that amplify the pressure gradient effects. Wyoming's Cody foothills, where gusts are forecast to reach 70 miles per hour, sit at the confluence of multiple terrain features that funnel airflow the way a nozzle focuses water from a hose. The wind that arrives there is not just the pressure gradient wind. It is the pressure gradient wind after the terrain has squeezed and accelerated it. But here is the critical timing issue, and this is the paradox at the centre of today's event. The phase of a cold front passage that produces the most extreme fire weather conditions is the prefrontal phase, the period before the front actually arrives. During this prefrontal window, temperatures are at their maximum for the day, relative humidity is at its minimum, and the pressure gradient winds are reaching their peak speed. The front has not yet delivered its associated precipitation. The cooling has not yet occurred. You're in a window where the warming and drying effects of the air mass ahead of the front are still fully active, but the winds generated by the front's approach are already accelerating, hot, dry, windy, maximum fire weather conditions, and this window is measured not in minutes but in hours. Then the front passes. The winds often shift direction abruptly, sometimes by 90 degrees or more, as the cold air behind the front takes over. Temperatures drop. In some areas, precipitation follows. The relief begins. But between the arrival of the front's leading edge and the arrival of meaningful precipitation, there can be a gap of hours, a gap during which the wind has shifted and accelerated but the rain has not yet fallen. If fires are burning during that gap, they now face a sudden change in wind direction that can cut off escape routes, reverse fire progression, and produce erratic behaviour that is extremely difficult to anticipate. The prefrontal environment today, the hottest, driest phase, is occurring right now, during the afternoon hours when temperatures are highest and humidity is lowest. The winds already driving across the corridor are not the arrival of relief. They are the announcement that relief is coming, combined with the worst possible fire conditions in the meantime. Think of it this way. The same system that will eventually lower temperatures and moisten the air is, right now, acting as the delivery mechanism for the most extreme fire weather of the entire event. The relief system is the risk multiplier. That is the cold front paradox of March 30th. And the trigger window it creates is exactly what the central thread of this story has been building toward. All of the pre-existing failures, the missing snowpack, the depleted fuel moisture, the months of drought, the record heat, all of them culminate in this atmospheric window. If ignition occurs now during this prefrontal maximum, it occurs under the worst possible conditions for containment and the best possible conditions for spread. Part 10. Wind shear, direction shifts, and fire chaos. There is a specific moment in a cold front passage that wildland firefighters have learned to fear above almost all other operational conditions, and it is not the strongest wind, it is the wind shift. Wind direction is the fundamental variable in how a fire behaves relative to the people fighting it. Every tactical decision made on a fire, where to build fire line, where to position crews, where to identify escape routes and safety zones, is built on an assumption about wind direction. The standard protocol is to work from the flanks of a fire toward the head, using the wind's direction to predict where the fire is going. As long as the wind is consistent, those predictions hold. Crews can position safely. Aircraft can drop retardant on the leading edge. The fire moves in a direction that, while dangerous, is at least predictable. A wind shift removes that predictability in an instant. When the cold front passes and the wind shifts direction, rotating from southwesterly prefrontal winds to northwesterly postfrontal winds, for example, what was the protected flank of the fire becomes the new head. What was the head of the fire is now the flank. Crews who were positioned to work the flank now find the fire advancing toward them from a new direction. Escape routes that were designed to move away from the predicted fire progression now route through the new fire's path. The margin between a manageable repositioning and a catastrophic entrapment can be measured in minutes. The behaviour of fire during wind shifts is non-linear in the most dangerous sense of that word. Fire behaviour models, the computer simulations that incident commanders use to project where a fire will be in the next hour, the next 6 hours, the next day, are calibrated to steady-state wind conditions. They assume that the variables driving fire spread will change gradually and predictably. A wind shift is a discontinuity. The models do not handle discontinuities gracefully. During the transition period, the window of 20 to 40 minutes when the old wind pattern is dying out and the new wind pattern is establishing itself, fire behaviour can become genuinely chaotic. Ember transport happens in multiple directions simultaneously. Spotting occurs unpredictably. The fire's perimeter, which was a line, becomes a cloud of potential ignition points ahead and to the sides of the main body. For today's event, this wind shift risk is not hypothetical. The cold front passage is a scheduled event on the forecast timeline. Incident commanders working any fires that ignite during the prefrontal window will be managing against a known, incoming wind shift that will occur at some point during their operational period. The question is not whether the shift will happen. The question is where their crews will be positioned when it does, and whether they will have enough warning to reposition safely. In normal fire weather conditions, experienced incident commanders manage wind shift transitions routinely. In the conditions of March 30th, with fire spread rates that could be measured in miles per hour under prefrontal winds, the response window for a wind shift is compressed to a degree that significantly increases the risk of losing control of the operational situation entirely. And here is the scenario that keeps fire behaviour analysts awake. Multiple fires, simultaneously active, across multiple states, all approaching the same cold front passage at roughly the same time, all experiencing the same wind shift at roughly the same time, all with incident management teams that are already stretched thin by the simultaneity of ignitions. Under these circumstances, fire behaviour does not just become unpredictable at the individual incident level, it becomes unpredictable at the system level. The mutual aid framework, designed to allow resources to flow from lower priority incidents to higher priority ones, breaks down when every incident simultaneously transitions to higher priority during the wind shift window. Part 11. Atmospheric stacking, rare alignment. Let me put all the variables on the table at once, because the reason March 30th crosses from significant fire weather event into genuinely rare territory is not any single number. It is the combination. Relative humidity at 8%. Check. Wind speeds at 30 to 40 miles per hour sustained. 70 miles per hour gusts in terrain channels. Check. Air temperatures 10 to 20 degrees Fahrenheit above historical March averages. Check. Energy release component at the 90th percentile, drier than 90% of all historically recorded days including peak summer months. Check. Dry thunderstorm potential providing natural ignition source. Check. Overnight humidity recovery forecast at Port Fair, meaning no natural reset cycle. Check. Fuel beds already depleted by a failed winter and 6 months of cumulative drought. Check. And this entire set of conditions aligned simultaneously across 1,500 miles of contiguous geography. Check. On any given fire weather day, even a bad one, forecasters typically see 2 or 3 of these variables elevated simultaneously. That is what produces a red flag warning, some combination of low humidity, high wind and dry fuels that creates conditions suitable for fire spread. The warning criteria exist precisely because these combinations are common enough to be worth flagging, but rare enough that each instance deserves attention. What is happening today is that every variable in that list has peaked simultaneously, every single one. Not 4 of 6, not 5 of 7, all of them. The statistical rarity of this kind of compound extreme event is not easy to communicate in simple terms, because our intuition about probability does not naturally handle the compounding of multiple independent variables. If the probability of any single variable being at an extreme level on a given March day is, say, 5%, then the probability of 2 variables being simultaneously extreme is roughly 0.25%, and 3 variables simultaneously is roughly 0.01%, and so on. By the time you are stacking 6 or 7 variables simultaneously, you're in probability territory that most historical records simply do not contain examples of. This is not a once-in-a-decade event. For March, this may be unprecedented in the instrumental record. Climatologists who study compound extreme events use a framework that describes how individual stressors amplify each other non-linearly. Each variable in today's setup does not just add its individual contribution to fire risk. Each variable amplifies the contribution of every other variable. The wind is more dangerous because the humidity is at 8%. If humidity were 25%, the same wind would produce dramatically lower fire spread rates. The low humidity is more dangerous because the ERC is at the 90th percentile. If the fuels were at normal March moisture levels, 8% humidity for a few hours would not reduce them to critical dryness. The high ERC is more dangerous because the wind is available to transport embers and deliver oxygen. Each factor multiplies the others rather than adding to them. This is what forecasters mean when they describe today's conditions as being in the extreme category, even for the most critical fire weather periods of peak summer. It is not that any single measurement is unprecedented in absolute terms. It is that the combination, the simultaneity, the mutual amplification of every variable simultaneously reaching extreme levels, that is what crosses into genuinely uncharted territory, and it is happening in March. Part 12. The overlooked variable, overnight recovery failure. In the normal choreography of fire weather, nighttime is the firefighter's ally. As the sun sets, temperatures drop, relative humidity rises, and the atmosphere releases some of the extreme drying it has been imposing on vegetation all day. The grasses and brush absorb some of that humidity back. The energy release potential of the fuel bed decreases slightly. Fire behavior moderates, spread rates slow, flame lengths decrease, ember transport distances shorten. Overnight is when crews can make progress on containment that would be impossible during peak afternoon conditions. It is when aircraft operations become less critical. It is when the fire gives you a small window to gain ground. The forecast for tonight's humidity recovery across the March 30th corridor is described in the National Weather Service briefings using language that translates to, "Do not count on it." The overnight recovery is forecast to be poor to fair, the lowest categories on the recovery scale. What does that actually mean? It means that the relative humidity tonight will recover only partially from the extreme daytime lows. Instead of the 25 to 40% overnight humidity that would allow meaningful fuel moisture recovery, the forecast suggests overnight values may only reach the teens, 12, 13, 15% in some areas. That is still critically low. Still below the threshold that allows fuels to recover to safe moisture levels. Still within the range where fire spread continues actively through the night. The mechanism behind this failed overnight recovery is the same heat anomaly that has been driving the entire event. When soil and air temperatures are 10 to 20 degrees Fahrenheit above historical averages for the date, the overnight cooling cycle cannot drop temperatures to the levels that would allow significant humidity recovery. The air retains too much sensible heat. The dew point temperatures, which determine the ceiling on nighttime humidity, are too high to allow the relative humidity to rise to recovery levels before morning solar heating begins the drying process again. You get a truncated recovery window, and even within that window the recovery is incomplete. For fire operations, this means no reset. The overnight period, normally the window during which containment lines can be reinforced, aerial retardant lines can be pre-positioned, and crews can rest while fire behavior moderates, provides none of those advantages tonight. Fires that are burning at 1800 hours will still be actively burning at 0200 hours. They will not be burning with the ferocity of the afternoon period, but they will not have moderated enough to allow aggressive containment work. Any ignitions that occur this afternoon will still be active fire events by morning, and by morning, the solar heating cycle begins again, pushing humidity back down toward daytime lows and reigniting the full intensity of fire behavior. This is the no-reset cycle concept that, when you string it forward over multiple days, produces the most exhausting and dangerous operational conditions in wildland fire management. Incident management teams are built around a roughly 24-hour operational period, with day and night shifts cycling against each other, and the overnight period providing the natural moderation that makes the night shifts work possible. Remove the overnight moderation, and you remove the operating assumption on which the entire incident management cycle is built. You get crews who cannot make meaningful progress at night, who face full intensity fire behavior again within hours of the day shift beginning, who are operating against a fire that has effectively never had a low activity period since ignition. Over multiple days, this produces a cumulative operational fatigue and resource depletion that goes beyond what the incident command system is designed to sustain. And here is the question that naturally follows from that. If one extreme fire weather day with poor overnight recovery strains the system, what happens when the underlying conditions driving that event are not temporary, not a single aberrant atmospheric pattern, but the expression of a long-term shift in the climate baseline? What happens if the no-reset cycle is not just tonight's problem? Part 13. The ENSO Transition Trap. The atmosphere does not operate in isolation from the ocean. The largest year-to-year driver of global weather patterns is the El Niño Southern Oscillation, the periodic warming and cooling of the central and eastern Pacific Ocean that reorganizes the jet stream, the storm tracks, and the precipitation patterns across much of the planet. The period leading up to this winter has been characterized by a La Niña pattern, cooler than average Pacific Ocean temperatures, which historically correlates with drier and warmer conditions across the American Southwest and Northern Great Plains. La Niña winters are the winters when snowpack underperforms. They are the winters when the storm track stays north of the Rockies and the mountain west goes dry. The current transition from La Niña toward neutral or El Niño conditions is relevant to March 30th because of what climate scientists call drought inheritance. Even when the ENSO pattern transitions toward a wetter phase, the moisture deficits accumulated during the preceding dry phase do not immediately reverse. Soils that have been in drought for months do not recharge overnight when the first above normal precipitation event arrives. The vegetation that has lost moisture does not restore it in days or weeks. The snowpack that did not accumulate this winter cannot be retroactively filled in by spring rains. The transition creates a period of atmospheric instability, variable and uncertain conditions, overlaid on a landscape that is still carrying the full moisture deficit of the La Niña period. That combination is the ENSO transition trap, and it is the background oceanic condition that enabled the snowpack failure that made March 30th possible. Part 14. Infrastructure on the edge. Fire is not the only system under stress today. The conditions driving the fire weather risk are simultaneously stressing infrastructure that, in a functioning system, would provide buffers against fire impact. Electric utilities in Wyoming, Colorado, and New Mexico are issuing precautionary public safety power shutoffs, deliberately cutting electricity to transmission lines in high-risk areas to prevent sparks from energized equipment becoming ignition sources. This is the same strategy that California utilities adopted in the aftermath of devastating fires attributed to transmission line failures, and it represents a recognition that the infrastructure itself has become a fire risk factor in extreme wind events. The water systems underlying this region are also carrying the stress of a failed winter. Lake Powell, the second largest reservoir in the United States and a critical water source for communities across the Southwest, entered this spring at levels that reflect years of below-average inflow, the direct result of the same snowpack failures that are driving today's fire risk. Water available for fire suppression, for emergency responders, for communities evacuated from fire zones, all of it draws from a water budget that has been running a deficit. These cascading connections between fire risk and infrastructure strain are the visible symptoms of the same underlying system failure that produced March 30th. Part 15. The controversy layer. Anytime conditions reach the level of intensity we're seeing today, and especially when they show up in a way that completely breaks seasonal expectations, the conversation doesn't stay confined to science for very long. It expands fast. People don't just ask what is happening, they start asking what could possibly cause something like this. And when the answer isn't immediately obvious or doesn't feel intuitive, the door opens to explanations that sit outside conventional science. That pattern isn't new. After major wildfire events, especially the ones that feel unprecedented, claims begin to circulate. Some point to geoengineering, large-scale climate manipulation programs altering weather patterns. Others suggest directed energy weapons, invisible systems capable of igniting fires or influencing atmospheric behavior. There are also broader ideas about atmospheric modification by governments or private actors, quietly shaping weather outcomes behind the scenes. These narratives don't appear randomly. They tend to surge under very specific conditions, when an event is unusually large, when its intensity exceeds historical norms, and when its timing feels fundamentally wrong. March 30th, 2026 checks all three boxes. The scale is massive, a continuous corridor of extreme fire weather stretching roughly 1,500 miles. The intensity is extreme, single-digit humidity, wind gusts approaching 70 miles per hour, and fuel conditions at the 90th percentile or higher. But the most destabilizing factor is the timing. This is happening in March, a month that, in many of these regions, is supposed to sit on the tail end of winter, not the front edge of fire season. When all of those elements converge, the event doesn't just feel severe, it feels out of place. And that sense of displacement is what fuels the search for alternative explanations. From a human perspective, that reaction makes sense. People build mental models of how their environment behaves. March means cooler temperatures, lingering moisture, maybe snowpack in higher elevations. It means a landscape that hasn't yet dried out. So when that same landscape suddenly behaves like it's in late August, when the air is drier than desert baselines, and the wind is strong enough to drive rapid fire spread, it creates a kind of cognitive dissonance. The observed reality doesn't match the expected pattern, and when that gap becomes large enough, the mind looks for an explanation that feels equally large. The key point, though, is this: the anomaly is real. But the mechanism behind it is not hidden, and it does not require external manipulation to explain. What's happening on March 30th can be traced step by step through processes that are well understood, directly measured, and physically consistent. There's no missing piece that requires speculation about secret technologies. Instead, what we're seeing is a chain of environmental conditions that, when combined, produce an outcome that feels extraordinary but is entirely explainable. Start with the foundation, the snowpack. In much of the western United States, snowpack is not just a seasonal feature, it's a critical component of the moisture cycle. Snow accumulates over the winter, storing water that is gradually released as temperatures rise. That slow release feeds rivers, replenishes soil moisture, and most importantly for fire behavior, rehydrates vegetation. It acts as a buffer, delaying the onset of dry conditions and suppressing fire risk well into the spring. In the winter leading up to March 2026, that system didn't function the way it normally does. Snowpack levels in states like Colorado and Utah were among the lowest on record. A majority of monitoring stations reported conditions consistent with drought. That means the expected recharge never happened. The moisture that should have been stored in snow simply wasn't there, and without that input, the landscape didn't get its seasonal reset. Instead, the drying process continued uninterrupted. That leads directly into the second factor: cumulative drought. Drought isn't just a snapshot of current conditions, it's a history. It reflects the balance or imbalance between precipitation and evaporation over time. By the time you reach late March 2026, large portions of the United States are already operating under significant moisture deficits. Soil layers are drier than normal. Vegetation is carrying less water. Even when conditions at the surface look stable, the underlying system is strained. This matters because fire behavior isn't just influenced by what you see on the surface. It's driven by the moisture content within fuels, grass, brush, trees, and within the soil that supports them. When that moisture content drops below certain thresholds, those fuels become far more receptive to ignition and far more capable of sustaining rapid spread. Then comes the third factor: heat. March 2026 has produced temperature anomalies across multiple states, with readings running 10 to 20 degrees above seasonal averages and, in some cases, setting records. Heat accelerates evaporation. It increases the atmosphere's capacity to hold water vapor, which in turn lowers relative humidity when additional moisture isn't available. It draws water out of soils and vegetation, pushing fuel moisture levels down even further. Think of it as a compounding effect. The snowpack didn't provide moisture. The drought ensured that existing reserves were already low, and the heat acted as an accelerator, removing what little remained at a faster rate than usual. By the time we reach the fourth factor, the atmospheric trigger, the system is already primed. That trigger comes in the form of a strong cold front moving into the region. On the surface, the idea of a cold front might suggest relief. Cooler air, maybe precipitation. But before that relief arrives, the front introduces a period of intense wind. Pressure differences between air masses create strong gradients, and those gradients drive airflow. In areas like the Cody foothills in Wyoming, terrain can amplify that effect, channeling winds and increasing their speed. At the same time, the prefrontal environment is typically the warmest and driest phase, so you have peak heat, lowest humidity, and strongest winds overlapping in a narrow window. That combination is what fire behaviour specialists look for when assessing extreme risk. And then there's the final piece, dry thunderstorms. Under certain atmospheric conditions, storms can form high in the atmosphere where moisture is present, but the air below is too dry for rain to reach the ground. The precipitation evaporates as it falls, a process known as virga, but the lightning still makes contact. That creates a scenario where ignition is possible without any natural suppression. In a landscape where fuels are already critically dry, even a single lightning strike can be enough to start a fire. When you connect all of these elements, the picture becomes clear. There is no single cause. There is no external system manipulating the outcome. What there is instead is alignment. The snowpack failed to deliver moisture. The drought ensured that the deficit persisted. The heat accelerated the drying process. The atmospheric trigger introduced wind and instability at precisely the moment when fuels were most vulnerable. And the potential for dry lightning provides a natural ignition source. Each of these factors is independently observable. Each can be measured, tracked, and analysed. And when they occur together, they produce exactly the kind of conditions that are now being forecast. In other words, the system is behaving exactly as it would be expected to behave under these inputs. What makes this situation unsettling isn't that it's inexplicable, it's that it's explainable, and that the explanation doesn't offer a simple fix. If the cause was something external, some kind of deliberate intervention, there would at least be a conceptual endpoint. Identify the source, expose it, stop it. But a system driven by environmental alignment doesn't work that way. There's no single switch to flip. The drivers are distributed across time and geography. They're embedded in seasonal cycles, climate patterns, and atmospheric dynamics. That's also where longer-term trends come into play. Changes in average temperature, shifts in precipitation patterns, variability in large-scale climate systems, these all influence the baseline conditions on which individual weather events are built. They don't guarantee that any specific event will occur, but they can make certain combinations more likely. They can increase the probability that the system reaches a state where extreme alignment is possible. So when people look at March 30th and feel like something doesn't add up, they're responding to a real signal. The calendar says one thing, the environment is doing another. But the explanation doesn't lie outside the system, it lies within it. The real cause is systemic environmental alignment. Multiple processes, each operating according to known physical principles, converging in a way that produces an outcome that feels extraordinary because it breaks with historical timing. And in many ways that's more concerning than any external theory. Because it means the system doesn't need help to produce extremes like this. It's capable of doing it on its own, given the right conditions. And those conditions, reduced snowpack, persistent drought, elevated temperatures and dynamic weather patterns, are not isolated anomalies. They are part of a broader pattern that is being observed, measured and studied. That doesn't make events like March 30th inevitable. But it does mean they are possible. And as the underlying conditions continue to evolve, the range of what is considered normal may shift with them. So the anomaly is real. The disruption to expectations is real. But the explanation doesn't require hidden mechanisms or unseen actors. It requires understanding how multiple environmental systems can align in ways that amplify each other. And once that alignment happens, the outcome isn't mysterious, it's inevitable. Part 16. Why this was predictable, but ignored. On February 15th, 2026, 43 days before March 30th, the National Weather Service issued its earliest red flag warning of the year across portions of the central Great Plains. On paper, that matters. In practice, it barely registered. It showed up in local bulletins, maybe a short segment on regional broadcasts, but it didn't move beyond that. No national pickup, no sustained coverage, no sense that this was anything more than a seasonal anomaly, an early flicker of fire weather in a year that would eventually normalise. But that framing, early but isolated, was the first misread. Because February 15th wasn't an outlier, it was the opening signal. Between that date and March 30th, the escalation didn't spike suddenly. It didn't jump from calm to crisis in a single step. It moved steadily, almost quietly, through a series of indicators that, taken together, told a consistent story. The problem wasn't a lack of data. The problem was that the data unfolded in a way that didn't trigger attention. Think of it like watching a reservoir drain, not in a single collapse, but millimetre by millimetre. If you look once, it seems fine. If you look every day, the change is obvious. But most people aren't looking every day. the drought maps were updating weekly. Each release from the US Drought Monitor showed incremental expansion, areas shifting from moderate to severe, severe to extreme. Nothing about those maps was hidden. They were publicly available, widely distributed, and technically clear. But they changed slowly enough that they never created urgency. There was no single frame you could point to and say, this is the moment everything changed. It was a gradient. At the same time, fuel moisture readings were deteriorating. Stations across Colorado, Wyoming, and the broader plains were recording values that fire behavior analysts track closely. Numbers that indicate how much water is held within vegetation and surface fuels. Over the course of February into March, those readings crossed into the 90th percentile dryness range in multiple basins. That's not just dry, that's top-tier dryness relative to historical records, the kind of baseline you expect to see deep into summer, not at the end of winter. Again, the data was there, but unless you're specifically trained to interpret fuel moisture thresholds, those numbers don't translate into immediate concern. There's no intuitive hook, no visual drama, just a line on a graph crossing a boundary that only specialists recognize as dangerous. Then there's the Snowpack. Throughout the winter, SNOTEL monitoring stations, automated sensors that measure snow water equivalent, were updating daily. Their data feeds directly into federal databases. Anyone can access them. And those readings were showing, in real time, that the snowpack across large portions of the West was not just below average, it was historically low. In some areas, it was functionally absent. For hydrologists and fire weather researchers, that's a red flag of a different kind. Snowpack isn't just about skiing conditions or reservoir levels, it's about delayed moisture release. It's about the system that carries water forward into spring and early summer, buffering landscapes against rapid drying. When that system fails, the consequences don't appear immediately. They unfold over months. But the trajectory becomes clear early. By late February and early March, that trajectory was already being discussed in professional circles. Fire weather analysts, land management agencies, and meteorologists were flagging the potential for an unusually early and severe fire season. Not publicly, in dramatic terms, but internally, in briefings, in technical discussions, in forecast outlooks that are read by other professionals. This is the part that's easy to miss from the outside. The warning system was active. The data was being generated. It was being transmitted through the appropriate channels. It was being interpreted by people who understood exactly what it meant. Within those networks, March 30th wasn't a surprise. It was a scenario. But outside those networks, the signal never fully translated. That disconnect, the space between institutional awareness and public awareness, isn't a failure of science. It's a feature of how slow-moving risks are communicated, or more precisely, how they aren't. Slow disasters don't trend. A snowpack dropping from 60% of average to 40% over 6 weeks doesn't create a headline that sustains attention. It's a gradual decline, not a sudden collapse. It doesn't produce images that circulate widely. There's no visual equivalent of a hurricane landfall or a wildfire front. It's just numbers updating quietly. The same is true for fuel moisture. When a station reading crosses below a critical threshold, that's meaningful to a fire behavior analyst. It's a shift from one operational category to another. But to the general public, it's invisible. There's no immediate consequence attached to that number in a way that feels urgent. Even the heat signals early on were framed in familiar terms. A warm day in early March, then another, then a record here, a record there. But weather records are broken all the time, and unless they're framed as part of a larger pattern, they don't necessarily trigger concern. They become isolated anecdotes rather than pieces of a system-wide shift. So the information was present, but it was fragmented. And that fragmentation matters, because people don't respond to isolated data points. They respond to narratives, clear, cohesive explanations that connect multiple signals into a single, understandable story. That story didn't fully emerge in the public space until March 30th, when everything aligned at once. By then, the drought had expanded. The fuels were critically dry, the snowpack deficit was locked in, the heat had accelerated the drying process, and the atmospheric trigger, a strong wind event combined with low humidity and potential dry lightning, brought all of those underlying conditions to the surface in a way that was impossible to ignore. That's what turns a slow disaster into a fast one, and that's where the concept of a predictable surprise comes in. A predictable surprise is exactly what it sounds like. an event that can be anticipated based on available data, but that still arrives with the social impact of something unexpected. Not because it couldn't be seen coming, but because the signals leading up to it didn't translate into widespread awareness or action. March 30th fits that definition with uncomfortable precision. Every step in the escalation was visible. February 15th, earliest red flag warning on record treated as an anomaly. Late February, drought intensifies across the west. Early March, fuel moisture drops into extreme percentiles. Mid-March, temperature records fall across multiple states. Late March, fire weather watches begin expanding across regions. March 30th, full alignment, warnings across 9 states, extreme conditions activated simultaneously. There's no missing data in that sequence, no hidden variable, it's a clear progression, and yet, from the perspective of the general public, March 30th feels sudden, abrupt, almost out of nowhere. That's the gap, not between science and reality, but between information and attention. The systems designed to detect and communicate risk did their job. They identified the signals early, they tracked the escalation, they issued warnings through established channels. But those channels are optimized for specific audiences, emergency managers, land agencies, specialists, not for broad public engagement over long timelines. By the time the message reached a wider audience in a way that felt urgent, the event was already underway, and that has implications beyond this single day. Because the environment we're dealing with now, one where multiple systems can align to produce extreme outcomes outside their expected season, doesn't just increase the risk of events, it compresses the timeline between early signal and full impact. If March 30th represents a predictable surprise with weeks of lead-up that went largely unrecognised, the question isn't just why did this feel sudden, it's what happens when the next one develops faster. What happens when the gap between the first warning signal and the full alignment of conditions isn't 43 days but 20, or 10, or 5? Because the limiting factor isn't our ability to measure the system, it's our ability to translate those measurements into awareness quickly enough to matter. That's the structural challenge, and it's not unique to fire weather. It applies to any slow-building risk, droughts, heat waves, even certain types of storms, where the early indicators don't carry the same weight, visually or emotionally, as the final event. So when March 30th feels like it arrived without warning, it's not because there was no warning, it's because the warning didn't take a form that demanded attention early enough. The instrument spoke, the data was clear, the trajectory was visible, but the story, the one that connects those signals into something people can act on, didn't fully surface until the system had already crossed into a state where action becomes reaction. And that's the part that matters going forward. Because if this was predictable, then the challenge isn't just understanding the science, it's closing the gap between what we know and what we respond to. Otherwise, the next predictable surprise won't just feel sudden, it will be. Part 17, a fire season. That started 90 days early. The historical fire season across the central and western United States follows a rhythm that, until recently, felt almost clockwork in its predictability. It is anchored in the annual snow cycle and the slow transformation of landscapes from wet to dry. In most regions, meaningful fire activity does not begin in earnest until late May or June. That's when snowpack has largely melted, soils begin to lose their stored winter moisture, grasses cure and vegetation transitions from living fuel to flammable material. The peak of that cycle traditionally arrives in July and August, when heat, dryness, and wind potential align most consistently. By September and October, cooler nights and shorter days begin to suppress that energy, gradually closing the window of high fire activity. That timeline is not arbitrary. It is physically enforced by the hydrological system of the western US, a system built around snowpack accumulation in winter and gradual release in spring. In a normal year, March sits on the far upstream edge of that process. It is still part of the recharge phase. Snow is still present in many basins, soils are still recovering moisture, vegetation is still transitioning from dormancy. Fire behavior at scale is typically limited by one dominant factor: insufficient fuel dryness and insufficient continuity of dry fuels across large landscapes. March 2026 breaks that structure in a way that is difficult to overstate. What is unfolding now is not simply an early fire season. It is a seasonal compression event. Conditions that historically belong to the height of summer fire activity are appearing in late March, approximately 90 days ahead of their expected peak window. The significance of that shift is not just temporal, it is structural. Because when peak conditions arrive at the start of the season rather than the middle, the entire architecture of risk response and recovery is forced into a different configuration. The conditions currently being observed, energy release component values in the 90th percentile or higher, critical fire weather designations from forecasting centres, multiple simultaneous red flag warnings across a 9-state corridor are not marginal indicators. These are peak-tier fire environment metrics. In a typical year, they cluster in July or August, when fuels are fully cured and atmospheric dryness is sustained over long periods. Seeing them in late March means the system is not ramping up toward peak intensity. It has already reached it. This creates a fundamental inversion of the fire season curve. Instead of a gradual build-up to maximum risk, the system has entered maximum risk immediately, and that inversion has cascading implications that extend far beyond the weather itself. The first and most immediate consequence is duration. If the fire season begins at peak intensity in March and follows even a historically average trajectory of atmospheric drying and fuel availability, the period of elevated fire risk does not resolve in early summer. It extends through the entire warm season cycle. Instead of a 3 to 4 month peak window, the system is now potentially operating within a 6 to 7 month high-risk envelope. That stretches from late March through October, with very little opportunity for meaningful recovery in between active fire weather periods. That extension alone changes the fundamental math of suppression. Wildfire response in the United States is built around a resource model designed for seasonal concentration. Agencies like the US Forest Service, interagency hotshot crews, state forestry divisions, and contract aviation assets operate on the assumption that the most intense demand will cluster within a defined summer peak. Aircraft contracts, personnel rotations, equipment maintenance cycles, and interagency mutual aid agreements are all structured around that expectation. When the peak period expands beyond its historical bounds, the system does not automatically scale. Instead, it absorbs stress. That stress shows up first as fatigue. Crews that would normally rotate through multiple assignments over a concentrated season are instead deployed earlier and for longer durations. Aircraft that would normally cycle through maintenance windows during shoulder seasons remain in near constant operation. Incident management teams that are typically assigned to discrete events begin overlapping responsibilities across multiple simultaneous fires over extended periods. And because fire suppression is not just about initial attack but sustained containment, the compounding effect becomes critical. Each additional week of elevated fire activity reduces the available buffer for recovery and preparation before the next wave of risk arrives. The second major consequence is what happens before fires even start: preparedness. In a normal seasonal progression, communities across the western United States use the spring months as a ramp-up period for mitigation. Prescribed burns are conducted under controlled conditions to reduce fuel loads. Fire departments clear defensible space around infrastructure. Local governments test evacuation routes and communication systems. Public awareness campaigns begin to circulate as summer approaches. But when fire weather conditions arrive in March at peak intensity, that preparation window is effectively disrupted. Prescribed burning programs, for example, are highly sensitive to atmospheric conditions. They require specific humidity ranges, wind limits, and fuel moisture thresholds to be safely executed. A landscape already experiencing red flag conditions cannot safely support widespread prescribed fire operations. That means a key tool for reducing future fire intensity is temporarily removed from the system just as it is most needed. Similarly, community-level preparedness is not yet fully activated. Messaging cycles have not reached their seasonal peak. Evacuation planning drills are not yet widespread. Even simple behavioral adaptations like clearing brush or reviewing emergency plans are typically associated with late spring or early summer awareness campaigns. An extreme fire weather event in March arrives before those behavioral systems are fully engaged. This creates a timing mismatch between risk and readiness. The third consequence is resource pre-deployment under uncertainty. When agencies like the National Interagency Fire Center assess early season risk, they typically scale resources gradually. Aircraft are positioned, crews are staged, equipment is distributed based on forecasted need. But when extreme conditions appear at the very start of the season, there is no lower baseline to build from. The system is forced into a high deployment state immediately. That means the same resources that would normally be stretched across a peak summer period are now being consumed at the beginning of the operational calendar. The implication is straightforward but serious. If early season demand matches or exceeds peak season expectations, there is no reserve capacity left for escalation later. And escalation is not hypothetical. It is built into the structure of the fire season itself. Because the fourth consequence of a compressed fire season is not just operational strain, it is probabilistic amplification. Fire seasons are not linear systems, they are compounding systems. Early season fires precondition landscapes. They alter fuel continuity. They create patchworks of burned and unburned terrain that influence how later fires spread. They also consume suppression resources that would otherwise be available for later incidents. So when a season begins at peak intensity in March, it does not simply extend the period of risk. It reshapes the landscape through which future fire events will move. That raises the central question for every fire behaviour analyst, meteorologist and land management agency currently tracking these conditions. What does summer look like if March already represents peak fire weather? The answer is not a single prediction, it is a set of conditional outcomes. If precipitation patterns return to near normal levels in late spring, there may be temporary relief. But that relief would arrive on landscapes already desiccated by early season heat and wind exposure. If drought conditions persist, the system does not reset, it accumulates stress. And if atmospheric patterns continue to favour high-pressure ridging and low humidity events, the frequency of critical fire weather days does not decrease as summer approaches, it increases. That is the structural concern. The baseline has shifted upward before the seasonal peak has even begun. In that context, March 2026 is not just early. It is foundational. It establishes the starting conditions for everything that follows. And those starting conditions matter more than they normally would, because they are arriving without the buffer that typically separates seasons. There is no gradual ramp. There is no extended period of recovery between winter moisture and summer dryness. The system has transitioned directly from one extreme state into another. This is where the planning challenge becomes most acute. Fire agencies are no longer just responding to events. They're attempting to manage a moving baseline. Every new red flag warning, every expansion of drought classification, every fuel moisture reading that remains at elevated dryness levels shifts the assumptions underlying operational planning. And those assumptions matter, because they determine everything from staffing levels to aircraft contracts to interagency coordination timelines. So the central issue is not simply that March is behaving like August. It is that August-level conditions are arriving at the very beginning of the system's operational cycle. That inversion compresses response time. It increases cumulative exposure. It reduces the margin for error in both prediction and suppression. And it forces every agency involved to operate under a scenario where historical patterns no longer provide a reliable guide for future behaviour. Which brings the focus back to the core uncertainty: escalation potential. If March represents the starting point, and the starting point is already at peak intensity, then the traditional concept of fire season peak may no longer apply in the same way. Instead of a single crest in midsummer, the system may now be operating on a flattened or extended high-risk plateau, where multiple peaks occur across a longer time window. And that is the question that cannot be answered yet, but must be planned for immediately. What happens when the peak is no longer a peak at all, but a baseline that lasts the entire season? Part 18. The new fire behaviour threshold. Something has been changing in the way large wildfires behave, and it's one of the most important shifts in fire science that has quietly accumulated over the last decade. It hasn't fully entered public awareness, and that gap matters more than most people realise when trying to interpret events like March 30th, 2026. Because what looks, from the outside, like extreme fire weather is only part of the story. Beneath it is a deeper structural change in how fire itself behaves once it reaches a certain threshold. Fire scientists often describe this as a threshold shift in fire behaviour, a point at which fires stop behaving like controllable incidents and start behaving like self-organising atmospheric systems. For most of the history of organised wildland fire suppression in the United States, roughly the past century, fire behaviour largely remained within an envelope that suppression systems were designed around. Fires were dangerous, unpredictable at times, and absolutely destructive, but they were still, in principle, manageable. A small ignition could be rapidly attacked. A developing fire could be boxed in with hand lines and dozer lines. Aircraft from agencies like the US Forest Service or contracted fleets could drop retardant to slow forward spread. Incident commanders could coordinate resources in a way that assumed a central truth. If you arrived early enough and with enough force, you could control the fire. That assumption didn't mean suppression was easy, it meant it was structurally possible. But beginning in the early 2000s, that assumption began to erode. And it didn't collapse in a single moment. It degraded through a series of fire seasons where something new began appearing with increasing frequency. Fires that no longer behaved like traditional surface-driven events. Fires that didn't respond to suppression in predictable ways. Fires that escalated faster than models expected. This shift is now strongly associated with what fire behaviour research defines as plume-dominated fire behaviour. To understand why that matters, you have to understand what changes at the threshold. In a conventional fire, the atmosphere controls the fire. Wind direction determines spread. Humidity influences intensity. Terrain modifies movement. Suppression tactics assume that external conditions dominate the fire's behaviour. But in a plume-dominated fire, that relationship flips. The fire begins to control the atmosphere around it. It generates a powerful vertical column of rising heat, an updraft so strong that it begins to create its own localized weather system. Air is drawn into the base of the fire with such force that winds become self-generated. The fire no longer depends on regional wind conditions to spread. It manufactures its own. In this regime, suppression becomes fundamentally constrained. Air tankers cannot safely operate near the fire's core because turbulence makes accurate drops impossible. Even large retardant aircraft are forced to work at distances where effectiveness drops sharply. Ground crews face even greater limitations. Fire lines built by hand or machine are overtaken not by steady flamefront movement, but by spotting events, embers lofted kilometres ahead of the main fire body. At that point, the concept of a fire perimeter begins to break down. The fire is no longer a single advancing edge. It is a distributed ignition field, and this is where the threshold shift becomes critical. Because what determines whether a fire enters this regime is not just ignition. It is a combination of variables that form a tightly coupled system: fuel moisture, atmospheric dryness, wind shear, terrain, and most importantly, energy availability within the fuels themselves. This is often quantified through metrics like the Energy Release Component, ERC, a key fire danger index tracked across the western US. ERC reflects how much potential energy is available in the fuel bed if it burns. Higher values indicate drier fuels and more intense fire potential. Historically, only the most extreme summer conditions pushed ERC into ranges associated with plume-dominated behaviour. But what fire researchers have been documenting over the past decade is that this threshold is no longer stationary, it is shifting. As drought conditions persist longer across landscapes, as winters deliver less consistent snowpack, and as vegetation cycles are disrupted by heat and moisture deficits, fuels are reaching critical dryness earlier in the year and maintaining it for longer periods. That means ERC values that once represented peak summer extremes are now being reached in shoulder seasons, or, as in March 2026, at the very beginning of the fire calendar. This is where March 30th becomes scientifically significant in a way that goes beyond weather reporting. Because what is being observed across the central and western United States is not just high fire danger, it is peak-tier fire behaviour potential occurring at seasonal minimum timing. That combination matters because it collapses the traditional separation between ramp-up and peak. Instead of a gradual increase in fire intensity as summer progresses, the system is entering high-intensity conditions immediately. And when high-intensity conditions arrive early, they don't just extend the season, they reshape its entire structure. But the most important and least intuitive part of this shift is that it is not one-directional, it is self-reinforcing. Extreme fires don't just respond to environmental conditions, they actively change them. When a high-intensity fire moves through a landscape, it fundamentally alters the fuel architecture. Surface vegetation that would normally act as a moisture-retaining layer is removed. Trees that provide shade and reduce soil evaporation are killed. organic layers in the soil are consumed or destabilized, and critically, large amounts of standing dead material, snags, are left behind. Those snags are not inert. They dry out over time and become highly flammable vertical fuels that can contribute to future crown fires. In other words, the aftermath of a severe fire creates conditions that increase the likelihood of another severe fire. This creates a feedback loop. Extreme fire burns landscape. Landscape becomes drier and more structurally vulnerable. Future fires ignite more easily. Future fires reach extreme behavior faster. Cycle repeats with increasing intensity. Over time, this loop shifts the baseline. What was once an extreme outlier becomes a more common state. And what was once a rare plume-dominated event begins to appear under conditions that would not historically have supported it. That is the deeper implication of March 30th. It is not just a day of extreme fire weather, it is a point on a trajectory. Fire behavior research over the past decade has increasingly documented that large fire events in the western United States are not only becoming more frequent, but also more likely to exhibit these threshold crossing behaviors earlier in their development. Fires that reach plume-dominated states are not just larger, they are fundamentally less controllable. They operate outside the assumptions built into suppression doctrine, and that creates a strategic mismatch. Because the modern fire suppression system, built through agencies like the National Interagency Fire Center and coordinated across federal, state and local partners, was designed around a different fire regime. It assumes that early attack can succeed. It assumes that extreme behavior is rare and concentrated in predictable seasonal windows. It assumes that atmospheric conditions will occasionally exceed thresholds, but not that those thresholds will shift permanently. What the data now suggests is that those assumptions are under stress. And March 30th is not an isolated anomaly in that dataset. It is a continuation of a pattern that has been building for years. When you line up major fire seasons over the past 2 decades, a clear signal emerges. Fires are not just becoming larger on average, they are becoming more likely to escape suppression earlier in their life cycle. The window between ignition and uncontrollable spread is shrinking under extreme conditions. That shrinking window is one of the most important operational challenges in modern fire management, because it reduces the effectiveness of the most powerful tool in the system, rapid response. If a fire reaches plume-dominated behavior within hours instead of days, then the entire structure of dispatch, mobilization, and containment planning is disrupted, which brings the focus back to March 30th. Because what is being observed across this event is not just a collection of extreme weather variables, it is a convergence of conditions that align with the very thresholds fire scientists use to define uncontrollable fire behavior. Low humidity, high wind speeds, critically dry fuels, and atmospheric instability are not separate risks, they are multiplicative. And when they align, they do not produce a linear increase in fire danger, they produce a regime shift. That is the central concern emerging from current research, that the fire environment itself is transitioning, not gradually, but through repeated threshold crossings that reset what normal looks like. Which leads to the most difficult question embedded in all of this. If conditions that once represented the upper bound of fire behavior are now appearing at the start of the season, then what happens when the actual peak conditions arrive? If March 30th is already operating near the edge of plume-dominated potential, then July and August are no longer just higher risk. They are potentially operating in an environment where the suppression envelope has already been exceeded before the season fully develops, and that reframes everything. Because it means March 30th is not just an extreme event, it is a baseline indicator. A signal that the system fire managers are working within is no longer the same system that defined the last century of fire suppression strategy. And once that baseline moves, everything built on top of it, response times, resource allocation, risk modelling, even public expectations, has to move with it. The science is not suggesting that fire suppression is obsolete. It is suggesting something more subtle but more consequential, that the conditions under which suppression works are becoming narrower, more conditional, and more dependent on early intervention than ever before. And that is why March 30th matters. Not because it is unprecedented in isolation, but because it fits a pattern that is no longer behaving like the past. Part 19. The Illusion of Relief. By the middle of next week, the forecast begins to look reassuring in a way that feels almost comforting after days of heightened concern. precipitation starts moving into parts of the corridor, temperatures ease down, and the strongest wind patterns gradually lose their intensity. The atmospheric setup that had been supporting rapid fire growth begins to break apart. As a result, red flag warnings are expected to be downgraded or cancelled in several areas, and with that shift comes something very predictable on a human level: a collective sense of relief. Weather apps stop showing alarming colour gradients, emergency alerts quiet down, and media attention moves on to whatever the next developing story is. It will feel for many people like the situation has resolved itself, but that sense of resolution is where the misunderstanding begins. The key issue is that atmospheric improvement and environmental recovery are not the same thing. What changes in the weather next week is temporary and fast-moving. What has changed in the landscape over the past months is slow, deep, and cumulative. And those two timelines do not reset together. The incoming precipitation will absolutely have an effect, especially on the surface. Dry grasses, leaf litter, and fine fuels respond quickly to moisture. These are the most visible parts of the system, and they are often the ones people intuitively associate with fire risk. When rain arrives, those fuels can temporarily regain moisture and become less receptive to ignition. That creates a real, measurable short-term reduction in fire spread potential. However, wildfire behaviour is not governed only by what is visible at the surface. Beneath that surface lies a much slower moving system: soil moisture, root zone hydration, and long-term vegetation stress. These deeper layers are what determine the moisture content of living plants, and they do not respond quickly to brief weather events. A passing rain system can wet the ground, but it cannot undo months of accumulated drought stress embedded in deeper soil layers. To understand this, it helps to think of the system less like a surface that gets wet and more like a reservoir that has been steadily drawn down over time. A short rain event is like adding a small amount of water back into a nearly empty basin. It changes the surface level briefly, but it does not restore the system to equilibrium. A more physical analogy makes this even clearer. Imagine a cast iron skillet that has been sitting over heat for a long time. If you pour a cup of water onto it, there is an immediate reaction: steam, sound, and visible change. It looks like cooling is happening, but the thermal energy stored in the skillet does not disappear. The water evaporates quickly while the metal remains hot. The system's deeper state has not fundamentally changed. That is what is happening in drought-affected landscapes after a short precipitation event. The surface reacts quickly, but the deeper moisture deficit remains. The heat, in this case, is not literal temperature but accumulated dryness stored in soils and vegetation. And that stored dryness is what controls how fuels behave when fire conditions return. This is why meteorologists and fire scientists distinguish between short-term weather relief and structural drought conditions. Structural drought refers to long-term moisture deficits in soils and vegetation systems. These deficits develop over months and sometimes seasons, and they require sustained periods of above-average precipitation to reverse. A single weather system, even a strong one, is not enough to rebuild that lost moisture. In the central corridor, the current models do not indicate that kind of sustained recovery. What they show instead is a passing disturbance, helpful at the surface, but limited in depth and duration. It may temporarily reduce fire spread rates, and it may create a brief window of lower fire weather risk. But it does not erase the underlying dryness that has been accumulating since the previous cool season. The scale of that deficit matters. Soil moisture losses across drought-affected regions are not measured in small increments. They are often measured in inches of water deficit distributed through deep soil layers. Restoring that balance typically requires repeated rainfall events over an extended period, along with reduced evaporation rates and consistent atmospheric moisture replenishment. Without that sustained input, the system remains in a depleted state even if surface conditions temporarily improve. This is where the distinction between live fuels and dead fuels becomes critical. Live vegetation depends on deep soil moisture to maintain internal water content. When that moisture is lacking, plants become more flammable from the inside out. Their tissues dry, their resistance to ignition decreases, and their contribution to fire intensity increases. A short rainfall event may slightly improve surface hydration, but it does not immediately restore the internal moisture balance of deeply stressed vegetation. Dead fuels, such as grasses and leaf litter, respond faster to rain but also dry out faster once conditions return to heat and wind. That means their temporary improvement is often short-lived. Within a matter of days after drying resumes, they can return to highly flammable states, especially under windy and low humidity conditions. This leads to one of the most important but least intuitive aspects of wildfire risk: the difference between temporary suppression of fire behaviour and actual reduction of fire potential. A rain event can suppress fire activity in the short term by increasing moisture in surface fuels and reducing immediate spread conditions. However, if deeper structural dryness remains unchanged, the potential for rapid fire growth returns quickly once atmospheric conditions become favourable again. Wind is especially important in this context because it acts as a force multiplier. In a dry system, wind accelerates evaporation, increases oxygen supply to flames, and drives rapid fire spread across receptive fuels. If the underlying landscape has not recovered moisture, then even moderate wind events can trigger significant fire behaviour. And in regions where wind events are a recurring feature of seasonal climate patterns, that means risk is not eliminated, it is only paused. The broader implication is that fire risk operates on at least two different timescales. The first is the event scale, where weather conditions such as wind, humidity, and temperature determine whether fires can start and spread quickly. The second is the structural scale, where long-term moisture availability, vegetation health, and fuel accumulation determine how intense those fires can become once they start. The midweek precipitation event primarily affects the first scale. It does not meaningfully reset the second. This distinction is often where public perception and scientific assessment diverge. From a lived experience perspective, rain feels like resolution. It interrupts fire activity, cools the air, and restores a sense of normalcy. But from a system perspective, it is only one input into a much larger moisture balance that has not yet been restored. That is why fire managers and researchers are cautious about interpreting short-term weather relief as long-term risk reduction. The underlying fuel bed, shaped by months of drought and heat stress, remains largely unchanged after a single passing system. The energy stored in that dryness does not disappear simply because the surface has been temporarily wetted. So when the next wind event arrives, and in this region, wind events are part of the normal atmospheric rhythm, it will be interacting with a landscape that has not fully recovered. The fuels will still carry the imprint of the long dry period. The soil moisture will still reflect a structural deficit. And the conditions that support rapid fire growth will still be present, even if they were briefly interrupted. This is the central distinction that often gets lost in the transition from crisis to calm. Event relief is visible, immediate, and emotionally powerful. Structural relief is slow, cumulative, and often invisible until it is complete. The problem is that wildfire risk is governed far more by the second than the first, and that is why the coming week's improvement, while real and meaningful in the short term, does not represent a reset. It represents a pause within a larger system that is still carrying the effects of everything that came before it. Part 20. The core mystery. Closing hook. Let us reassemble the chain one more time, not because any single piece is new, but because the meaning only becomes visible when the full sequence is held together at once. Each component on its own is already understood in science. Each variable has been measured, modelled, and discussed for years. But the story is not in the variables. The story is in what happens when they converge in the same narrow window of time, and that convergence is what March 30th represents. It begins in the mountains, quietly, in a way that would normally set the entire seasonal system in motion. Colorado and Utah record the lowest snowpack in their documented history. This is not a minor deviation or a slightly dry winter. It is the collapse of the seasonal water storage system that feeds the entire central corridor. In a normal year, snowpack functions like a delayed release reservoir. It accumulates water through winter, then releases it gradually through spring, saturating soils and supporting vegetation recovery exactly when the landscape begins to warm. That cycle is what normally delays meaningful fire risk until late spring or summer. But in this case, that reservoir is already empty before the system begins to draw from it. Roughly 80% of monitoring stations across the region enter drought conditions before winter even ends. That means the recharge phase of the hydrological cycle never properly completes. The system does not transition into spring with stored moisture. It transitions already depleted. That is the first structural imbalance, and it sets the baseline for everything that follows. On top of that, depleted baseline comes a second force: heat. Across 14 states, March temperatures run consistently 10 to 20 degrees Fahrenheit above historical averages. This is not a short-lived warm spell. It is sustained atmospheric forcing that changes the rate at which the landscape loses moisture. Soils that would normally be absorbing meltwater instead begin releasing it into a dry atmosphere. Vegetation that should be entering its spring recovery phase instead continues the drying process that began in the previous autumn. The seasonal reset that normally restores fuel moisture simply does not occur. By late March, fuel moisture readings begin to resemble something that, in historical records, would only appear in peak summer conditions, not early spring variability, not transitional dryness, full summer level desiccation in March. That alone would be significant, but it is only one layer of the system. Into that already stressed environment, a third forcing arrives. A cold front moves in from the northwest, interacting with an atmosphere that is already primed for instability. The pressure gradient ahead of the front tightens dramatically across a vast region spanning more than 1,000 miles. As that gradient strengthens, wind speeds increase steadily, reaching sustained levels of around 40 miles per hour in many areas. These winds are not isolated gusts. They are persistent system-wide flows that align with dry surface conditions. At the same time, the air mass becomes even drier. Relative humidity drops into single digits in many locations, reaching around 8% in some zones. This is not simply dry air in a general sense. This is an atmosphere actively extracting moisture from vegetation and soil at an accelerated rate. Under these conditions, any available fuel dries rapidly, and any ignition source encounters minimal resistance. Fire weather systems respond accordingly. The Storm Prediction Center introduces dry thunderstorm indicators, signaling the potential for lightning without meaningful precipitation. 16 red flag warnings are issued across multiple regions, alongside fire weather watches covering 9 states at once. These are not localized alerts tied to isolated incidents. They are large-scale signals that the atmosphere has aligned into a configuration capable of supporting rapid fire growth across a broad corridor. Fuel energy indices confirm the same picture. The energy release component reaches the 92nd percentile, indicating that the amount of energy available in surface and near-surface fuels is higher than nearly any comparable historical March condition. That means if ignition occurs, the potential intensity of fire behavior is already elevated before the fire even starts. And all of this occurs on March 30th. None of these individual elements is unprecedented on its own. Low snowpack years have occurred before. Extended drought cycles are part of the regional climate system. Record or near-record March heat has been documented in past decades. Strong wind events across the Great Plains are a regular feature of seasonal transitions. Dry thunderstorms are not unusual in certain atmospheric setups. Even high-energy release component values can appear in isolation under specific conditions. What is unprecedented is not the existence of any one of these factors. It is their simultaneous alignment within the same temporal and spatial window. The convergence is what transforms the system from a collection of stressors into a unified fire environment. This is where the system stops behaving like a set of independent variables and begins behaving like a coupled structure. Each factor amplifies the others. Low snowpack reduces long-term water availability. Heat accelerates evaporation and soil drying. Wind increases both oxygen supply and fire spread potential. Dry fuels lower ignition thresholds. Atmospheric instability increases the probability that any ignition will escalate rapidly. Together, these interactions produce a system that is far more volatile than any single measurement suggests, and that is the central issue. Not that the science is unknown, not that the mechanisms are mysterious. Each component is well understood. The issue is structural. It is about how often these components now align outside the historical window that once defined fire season. For most of modern fire management history, fire risk has been organized around a calendar. That calendar assumes that fire season is a bounded period. It begins in late spring or summer, intensifies through dry months, and declines with autumn moisture. That assumption has shaped everything from staffing cycles to suppression readiness, from public messaging to infrastructure design. The calendar acts as a proxy for risk, but March 30th challenges that proxy at a fundamental level. Because what is being observed is not just extreme weather within a season, it is seasonal structure itself becoming unreliable as a predictor of fire behaviour. Conditions that would traditionally be associated with midsummer intensity are appearing in early spring. The temporal boundary between safe season and fire season is becoming less distinct. This is not a matter of a single anomalous event. It reflects a longer-term trend in which background climate conditions are shifting the timing of fire-relevant variables. The snowpack failure is not random. The drought is not isolated. The heat anomalies are part of a broader pattern. March 30th is simply the moment when those trends become simultaneously visible in one coherent snapshot. The implication is not that fire behaviour is becoming unpredictable, it is that it is becoming less seasonally constrained. The system is still governed by physics, chemistry, and atmospheric dynamics, but the timing of when those dynamics align is changing. That is why March 30th is significant beyond its immediate impacts. The event itself will pass, the wind will weaken, humidity will partially recover, red flag warnings will be downgraded, the atmosphere will return to a calmer state. But the deeper conditions that allowed this alignment will remain largely unchanged. The snowpack deficit does not reverse in days, the soil moisture does not fully recover from a passing front, the fuel structure does not reset. What remains is a landscape that has already demonstrated its ability to reach extreme fire conditions outside the traditional peak season. That leads to the central question that follows this event. It is not about whether March 30th itself will escalate further. It is about what March now represents in the system. Because if March can produce conditions that match or exceed historical peak fire season behaviour, then the calendar-based model of fire risk is no longer sufficient on its own. It becomes a lagging indicator rather than a predictive tool. The instruments are now describing a system that is no longer fully aligned with the seasonal assumptions built into planning and policy. This is not a sudden break from the past. It is a shift that has been building gradually over time. But March 30th is one of those moments where the shift becomes visible enough that it can no longer be interpreted as background noise. The system is still moving forward. The calendar is still fixed in place. And the gap between the two is where the new fire reality is beginning to take shape.